All right, good morning, chemists. We'll get started. So as you see, the chemistry department has finally got our stuff together and figured out the schedule for next term. So I am teaching Chem 1220, the Tuesday, Thursday, 8 a.m. And I'm also teaching the 11:10 a.m. So, you can choose to follow me into the darkness. That is 1220 for next term, or, to stay away from these sections, because there are quite a few sections of 1220 for you to choose from. So, yep, that's what I'm teaching. So that's what you're waiting for. And just so you know, I will have an office hour after each of them. So depending on, what course you choose, if you're able to fit it in your schedule to have the next hour free, you'll be able to attend office hours. But of course, you can attend either of these. I'll post when those office hours are. All right, so that's my schedule. So the plan is maybe get close to the end of chapter 8 today, or finish chapter 8 on Tuesday. But I did want to point out next Tuesday is Halloween, and I have something special prepared for Halloween. So I am going to dress up. So I would love it if any of you guys would also dress up, maybe dress up as your favorite chem teacher and wear a nice sharp blazer and some colorful pants. That would be cool. But you guys are in college. You can do whatever you want. So this is like the last time you can have fun like this. So I will have something special that you've probably never seen before on Tuesday. So do come to class on Tuesday. All right. So let's continue on of our conversation of electronegativity, right? So electronegativity, we're forming chemical compounds, all right, in the form of covalent bonds. So we're sharing electrons, but I've introduced the idea that electrons are not always equally shared, especially when the two atoms you're bonding together are not identical. So we have to consider the electronegativity of the atoms that form our bond. Some elements attract electrons more than others, and so we have a couple trends. I just remember fluorine is the most electronegative, cesium least amount of electronegative, and so when you form a chemical bond, you need at least two atoms, and so when we compare the difference of electronegativity of those two atoms that make up the bond, can tell us the characteristics of that bond, whether it is a polar covalent bond. That's typically what we're going to work with in covalent molecules. We can have a purely non-polar bond if the electronegativity difference is really small. Or an ionic bond if it's very different. And so this brings on different characteristics that we'll talk about in chapter 9. And so my tip is when you have two elements that form a chemical bond and they're far away from one another on the periodic table, it means that their electronegativities are very dissimilar. So if they're dissimilar, if you subtract them from one another, you're going to get a fairly large difference. But if the two elements you're bonding together are close to one another on the periodic table, then they have more similar electronegativities. So if you subtract two numbers that are of similar values, you're going to get a small difference. And so that's the big idea there for us to predict electronegativity. All right, and then I showed some pictures on how we can demonstrate pictorially where electron density is. And so we have a purely nonpolar compound, polar covalent, and an ionic compound, and we see partial charges form for our polar compounds, where this part of our molecule where the fluorine lives is partially negative. That's why we have this delta sign, and a partially positive on the other side. So we can use these dipole arrows, which will come back a little bit later in chapter 9, dipole arrows to represent this separation of charge, where basically the magnitude of this arrow, essentially magnitude, how big the arrow is, how big this dipole arrow is trends with the difference in electronegativity of those two atoms. So larger electronegativity difference, larger dipole arrow, versus an element or compound that has no electronegativity difference. So here, this is our nonpolar compound. This substance has no permanent dipole within it. So we do not have to draw a dipole arrow for our fluorine molecule. All right, so let's look a little bit closer into this idea of partial negative, partial positive, portions on our chemical bond. And this brings us to the idea of dipole moment, which is a way we can quantify that dipole arrow that I mentioned before. So here we have a separation of charges. So if this was our polar molecule, we would say like this side is partially negative, this side is partially positive. And so since those charges are separated by basically a constant bond length, what we produce is this dipole moment. It's a separation of charges via some type of distance. Those two charges are separated by a distance. And so how we calculate dipole moment of this molecule or of this system is we just take the product of the charge separation times how far away they are from one another, so times radius. So dipole moment, mu here, the Greek letter is equal to Q times R, and so these two variables relate to things we've already talked about. Q is related to the electronegativity difference, the magnitude of difference of this charge separation, right? So, and R is related to the bond length or the atom sizes that constitute this chemical bond. So there's a couple of trends that we can kind of come up with. How do we increase or decrease dipole moment when it's measured in an experiment? This mu dipole moment value will increase when any one of these two values increase. If Q increases, charge separation increases, dipole moment increases. If R increases, then dipole moment increases. And you can see that in this graph here, or this table of different dipole moments of compounds. So we see as we go from HF to HCl, HBr, HI, we see that the measured dipole moment here actually decreases as we go down our periodic table. And so if we compare this to electronegativity difference and bond length, we see that as we go down the periodic table, bond length increases, but we see electronegativity difference decreases, that H and I have more similar electronegativities than H and F. And so we see here is that our electronegativity difference is what dictates this overall lowering of our dipole moment. Because we see radius is actually increasing as we go down, so we would think, oh, dipole moment would increase based upon our equation, but that's not what we see experimentally. So what we can conclude here is that the electronegativity differences of the atoms that make up that bond are more important in this example than actual bond length. All right, so that's how we can do it experimentally. So let's see if we can navigate this equation by me giving you just some examples here, some changes. How would our dipole moment of our system, so let's just take a look at this equation, if we shorten the bond between our two atoms? Shortening the bond changes which one of these variables, Q or R? R. So if R decreases, what happens to mu? Also decreases, and we're assuming everything else is staying constant. So if we shorten the bond, we see dipole moment will decrease in our system. All right, what if we lengthen the bond? So this time R is increasing, so we're separating these two charges further away from one another. Mu is going to change how? It's going to increase, again, because of our relationship here. What if we increase the electronegativity difference of our atoms in the bond? What's changing in our equation? And not R anymore. This time, changing electronegativity difference, we're actually changing Q, the Q component of this equation. And so we see that electronegativity difference is related to Q, so we should see Q increase. And so what we'll see is mu will also increase. Our dipole moment of our system should increase. And again, this is assuming everything else stays constant. All we're changing is just electronegativity difference. And then the last one here, as Q decreases, or if we change the identity of our atoms to lower our electronegativity difference but keep the bond length the same, we should see a decrease in our dipole moment. All right, so those are the trends. So let's see if we can put that together. So which molecule here, let's not show the answer, which bond here has the larger dipole moment? So I want to know which one has the larger mu, the NO single bond or the NO double bond? What do we think? So let's think of the two factors that relate to mu. It's Q and it's R. So in this example, What's changing between option A and option B? Q, which is related to our difference in electronegativity, or R, bond length. So which one changes? R changes, yeah, so it does, electronegativity difference does not change. In both bonds, it's an N and an O. So the difference is going to be the same in each of these examples. What's changing is our R value. So when we compare a single bond and a double bond is what compared to a double bond? It should be longer, yeah. So in the single bond, R is longer, while the double bond, it is shorter. So now, can you tell me which one has the larger dipole moment? A, yes, A has the larger dipole moment. For what reason? It has a longer bond. Yes, R is bigger, and so we see if R is bigger, then mu will be, overall dipole moment will be bigger in this example. Right, so that's how we approach that. I took it as, okay, both of them have N and O. They have the same difference in electronegativity, so Q is going to be the same, but the bond lengths are different, and we can relate that to dipole moment. This is an equation you are going to get on the supplemental information. I actually, if you noticed, did you notice what I posted? Yes, I posted all of the practice midterms for midterm 3, including the supplemental information. And so you'll see it's rather sparse this term. You get one equation and one crazy diagram that we will talk about in chapter 9. But there's very little calculations. Honestly, if you forget your calculator, it's not a big deal if you forget your calculator. Actually, I'm going to tell my TAs if they see people using their calculator in midterm 3, that's kind of sus. So, yeah. All right. Okay, so that's bond dipoles. Yeah, you don't need to use your calculator in chapter 3 or midterm 3. So we're going to draw Lewis structures now, and so I want to remind you we went from doing ionic compounds, looking at the Born-Haber cycle, utilizing ionization energy, electron affinity, all that stuff. Now we've switched to molecular compounds on nonmetals. This is where electronegativities are going to come into play. We need to think about bond polarities, especially going into chapter 9, but we're going to be drawing Lewis structures. There is a strategy for drawing Lewis structures. There's 6 steps, and I'm going to be referring to these 6 steps for the next 2 weeks. So it's in your best interest to just memorize them, because if you do these 6 steps, you will be right every single time. Because I remember in high school, when I had to draw Lewis structures, I didn't learn the 6 steps, all right? I would just draw my atoms, draw some bonds, and I would just keep drawing dots until I felt like stopping, all right? Never do you have to actually do that, all right? There's a system to how many dots you have to draw, how many double bonds, where to put those double bonds. There's a strategy to it, and you will always be right if you follow my 6 steps. You don't have to be like me and just spray and pray for drawing lone pairs around atoms. All right, so these are the steps. First, count the number of valence electrons on all of the atoms. So that is a chapter, 6, 7 concept. All right, so valence electrons. Depending on what molecule you're focusing on, if it's an ion, so like a cation or an anion, we have to remove or add electrons as necessary to make that charge. If it's a neutral atom, you can skip step 2. Or a neutral compound, you can skip step 2. This is only if it's an ion. Next, we draw our skeleton structure, where typically the first element that's written in the formula, 9 times out of 10, that's the central atom. All right, and we put that atom in the center, and then we draw all the other elements around it, all the other atoms around it. And we draw single bonds to all of those atoms. So usually the central atom is written first, unless it's hydrogen. But the real, indication of what the central atom is, it's usually the most electropositive element. But 9 times out of 10, it's the first element that's written in the formula, all right? So you draw it in the center, and then you draw all the other atoms around it. And then you draw single bonds. But remember, these single bonds, we talked about bonds. Bonds contain electrons. So for every bond you draw, how many electrons are represented in one single bond? 2 electrons, yes. Because the number that we get from steps 1 and 2, those valence electrons, those are the number of electrons you are allowed to draw on your structure. That's how much money we have to spend. So for every bond you draw, that's taking away from your valence electron count that you're allowed to draw. So we got to keep inventory of all of those electrons. All right, so after step 3, once you draw your skeleton structure, you will start to put any extra electrons that you have left over from our electron count on the outermost elements first and complete their octets. Then once we've completed octets, then we can move to the central atom, all right? And so that's step 5, we put them on the central atom, so outer first, then inner. And then finally, step 6, this step is important if you have elements, atoms that are octet deficient. It'll usually be your central atom, and that's when we start drawing double bonds. And I'll talk about that in a bit. So we'll draw double bonds in order to complete octets, and I'll show you some examples. So let's just do some examples. These are the 6 steps. All right. Here are just some tips. I'm going to skip this for now and come back to it later. But the big idea here is if you have hydrogen in a compound, it's only ever going to have a single bond. All right, single bonds. Hydrogen will never be the central atom. Also halogens, typically, if they're an outer atom, also have 1 bond. Those are ways to help you draw a Lewis structure really quickly. If you only have hydrogens or only have halogens, you can draw them rather quickly. And then I'll talk about double bonds and these exceptions in a little bit. I think I have some more tips down here. All right, I'll come back to this slide. So let's actually just do an example. All right, so let's do ammonia. Here is just our strategy. We need to count electrons, adjust for charge, write our skeleton structure. Then we need to place extra electrons on outer atoms first. And then if we have any left over, then we place electrons on our central atom. All right, so there's our strategy. So let's do it. Okay, so first step, count valence electrons. So I take inventory of all my atoms. So we have a nitrogen and we have 3 hydrogens. So nitrogen has how many valence electrons? 5, yes, where'd you get that? From the periodic table, nitrogen's group 5. Hydrogen has how many valence electrons? 1, but there's 3 of them. So we're gonna do 3 times 1. So each of those hydrogens have 1 valence electron. So we are allowed to spend 8 electrons in our picture. All right, so we did the first step, valence electrons. We adjust for charge. Do we have to do anything here? No, because ammonia is neutral, so we just skip this step. Next, we draw the skeleton structure, which means we figure out what the essential atom is, and then we draw the other atoms around it. So which of these atoms is my central atom? Nitrogen. Nitrogen is our central atom. You might be thinking, well, how do we know that? There's a couple things. Nitrogen is written first. Also, hydrogen is never going to be the central atom, and you'll see why. Okay, so nitrogen is our central atom. Then we draw the 3 hydrogens around it. Okay, and then we draw single bonds to each of them. So 1, 2, 3. All right, so in that process of drawing bonds, I actually used some of my electrons because remember, each bond contains 2 electrons. 1, 2, 1, 2, 1, 2. So I've spent how many electrons so far? 6. So how many do I have left over? 2. All right, so with those last 2 electrons that I still have to spend, this is where now I complete the octets of the outer atoms first, then the inner atoms. So let's look at the outer atoms first. They're hydrogens. According to our boy Gilbert Newton-Lewis, does hydrogen have a satisfied octet? Yes, it does, because what's the rule for the octet? I know we call it octet, so it means 8, but hydrogen is kind of an exception. Hydrogen only needs 2 electrons, and so because each of those hydrogens has a single bond to it, it has 2 electrons. So the hydrogens are good. We don't have to do anything to hydrogen. So since I still have those 2 electrons left, where are they going to go? On the central atom, so it's going to go on nitrogen. So when I put them on nitrogen, I put the 2 electrons on nitrogen. So I used up my 2 electrons, but what did I also do in that process? I completed the octet of nitrogen. Because if we count all of the electrons around nitrogen, there's 1, 2, 3, 4, 5, 6, 7, 8 electrons on nitrogen. So now all of the atoms actually have complete octets. Hydrogens have 2, that central nitrogen has 8 around it. And so we've spent all of our electrons, we check octets, this is our Lewis structure for ammonia, and we're done, right? Because we spent all our electrons and our octets are satisfied. So with this example, we did steps 1 through 5, and we didn't have to do step 6. So see how I say start making multiple bonds or double bonds if necessary. We'll only need to do step 6 if an atom is electron deficient, meaning that it does not have a complete octet, and we'll look at an example in a little bit. All right. Okay, so that's ammonia. Good? Good. All right, so let's do another one. Formaldehyde. Here I'm telling you carbon is the central atom. So I'm just trying to be explicit, but the real rule is the most electropositive atom is the central atom. All right, so what's my first step? Count electrons. So we got a carbon, we got 2 hydrogens, and an oxygen. So carbon has how many valence? 4, hydrogen, 2 times 1, oxygen, 6. What does that add up to? 12? 12. Okay, so we got 12 valence electrons to spend. I don't need to adjust for charge because formaldehyde is a neutral molecule, right? So we got 12. All right, what's the next step? Yeah, we got to do the skeleton. So I'll just copy this down here. Here we go. Copy that down there. All right, so we did valence, adjust for charge. Now we need to do skeleton. So what goes in the center? C. And then we just put everything else around it. Doesn't really matter where. So I'm just going to put the hydrogens like this. And then I put an oxygen and I draw a single bond. Single bonds to everything. All right? Okay, so if I was in high school, what I would do is just start drawing dots everywhere. That's what I would do. But that's not what we do here. We follow the 6 steps and we'll always be right. So I drew 3 single bonds. So how many electrons have I drawn so far? 6. I'm allowed to spend 6 more, right? So those 6 electrons are going to go on outer atoms first, then inner atoms if we have any left over. So let's do that. So the electrons are going to go where? On the oxygen. Because why don't I put them on hydrogens? They're already good. They're already good. So we're going to try to complete the octet of oxygen. So how many electrons does that oxygen have right now? 2. So I'm going to complete its octet by doing 1, 2, 3, 4, 5, 6. That's what I'm going to do. All right? So now does that oxygen have a complete octet? Yes, it does. Cool. And then, so if I was in high school, this is what I would have done. I'd be like, oh, oxygen has a complete octet, but carbon doesn't, so I'm going to draw 2 more electrons. Can I do that? No, because I ran out of electrons, so I can't draw 2 more electrons on that carbon, even though carbon is electron deficient. So this is where that last step, step 6, comes into play, right? So we placed electrons on our outer atom, oxygen, to complete its octet. We didn't have any electrons left over to place on our central atom, so now we need to focus on this. Make multiple bonds if we are electron deficient. So which atom is electron deficient? Carbon, all right? So here's the idea. We spent all of our electrons. We can't put any more on, but what we can do is move electrons around so they're shared between 2 atoms. So this is what I'm going to do. Carbon needs 2 more electrons. So I'm going to take 2 of the electrons on an adjacent oxygen atom, and I'm going to place it here. So there's 4 electrons shared between oxygen and carbon. So now I'm going to redraw this structure, but now the new thing is that carbon is going to have a double bond between oxygen. Do keep track of your electrons. Since I only moved 1 pair over, I still have 2 other pairs of electrons there, and then those hydrogens are still there. All right. So all I did to make carbon have a complete octet was move electrons around. I did not add any more because I ran out. I only have 12 electrons to spend. But what I can do is just move electrons around to make double bonds so carbon has a complete octet. So now we can check all of our atoms. Hydrogens have 2. This oxygen, so remember a double bond is formed from 1, 2, 3, 4 electrons. So if we look at this oxygen atom, there's a total of 8. And if we look around the carbon atom, does carbon have a fulfilled octet now? Yes, it does, where there's 2 bonds, 2 electrons in each of the single bonds, so there's 4 there. And then this carbon also has 4 electrons being shared with it with oxygen. So every atom now has a complete octet, and I did it by only using 12 electrons because that's all I'm allowed to do, right? And so that's that last step, making double bonds if needed. You get to this step and you recognize, oh, my central atom is deficient. Now I start making double bonds. All right, and so our correct Lewis structure is this one. All right, so it's very systematic, very systematic. Okay, do we have another one? No, we don't. Okay, so let's talk about other ways we can determine if a Lewis structure is most correct, and that's the idea of formal charges, that once we draw a Lewis structure, we're kind of telling the reader where we will find electrons on a molecule. And so an atom typically has a preferred number of electrons that it wants to have, and it's based upon its valence electrons on the periodic table. But sometimes how we draw a Lewis structure doesn't always match what an atom's preferred number of electrons is. So this is where we use formal charge to assign to an atom to figure out what is the charge of that atom in this drawn Lewis structure. So the idea of formal charge, it's the charge that an atom would have in that Lewis structure. But remember, in covalent or molecular compounds, there are no charges. It's not ionic. So this is kind of similar to ionic charges, but it's not really real. It's just a way for us to determine, is this structure plausible or not? So how we assign a formal charges, we'll do this to every single atom in a Lewis structure. What you want to do is count the number of electrons or indicate how many electrons an atom typically has. So this is the number of valence electrons for a certain element. All right, so if you're inspecting like a nitrogen typically has 5 valence electrons, so you'll put 5 right there. And then you want to subtract the number of electrons that are assigned to that nitrogen in the Lewis structure, all right, as you've drawn it. All right, so what you're going to do is count half of the bonding electrons and all of the non-bonding electrons around that atom, and that's what that's how we calculate a formal charge there. And so once we get the formal charges of all of the atoms in the structure, we can determine, especially if there's more than one correct way to finish a Lewis structure, what we want to do is pick the Lewis structure that minimizes formal charges. 0 is a preferred formal charge for an atom in a Lewis structure, or if we have to have a formal charge, so like a negative formal charge, we want the structure that puts that negative formal charge on the most electronegative atom. Or if there's a positive formal charge present, it's on the least electronegative atom. All right, so let's just do some examples and hopefully it'll all come together. All right, so here's the equation for a formal charge. You will not get that on the exam, but here's another way to think about it. Right, to calculate formal charge for each atom, you want to think about how many electrons does an atom want. That comes from the periodic table. And you want to subtract the number of electrons that that atom has in the Lewis structure. All right, so that's the equation. Formal charge equals once minus has. But there's some caveats here, all right? That this has idea, this has electrons, it's where each bond, so if we look at like nitrogen here, when we calculate that has number, what we want to do is remember that that chemical bond has 2 electrons in it, and so what we're going to do is assign one electron to each of those atoms, and we'll do that to each one of these chemical bonds. So if we look at this molecule, the number of electrons that this hydrogen atom has is 1. The number of electrons that this hydrogen has is also 1, and same thing for this. But if we look at nitrogen, if we put a box around nitrogen, how many electrons are on this nitrogen atom in this Lewis structure? How many dots are inside that box? 5, all right? So we're splitting, if you go back to the equation, it's half of your bonding electrons, but all of the non-bonding electrons, all right? So that's what we did in this box. We only took half of its bonding electrons, but we used all of its non-bonding electrons. All right, so I'll show you how I calculate formal charges. It's once minus has, and so what I typically do is I make a table. And so I'm looking at the nitrogens first, then I'm going to look at the hydrogens. And so I determine how many electrons does each of these atoms want. And then I subtract how many electrons that each of those atoms have, the number of electrons that are in each of those green boxes that I've drawn here. Right? So nitrogen typically wants how many electrons? 5, yeah, so this comes from your valence electrons count, right? So your number of valence electrons from your periodic table. So nitrogen wants 5, hydrogen typically wants 1, yes. So now let's look at the Lewis structure and count the number of electrons that each of those atoms have. So nitrogen in this structure, how many dots are in that box? 5, and then hydrogen has 1. So when we subtract these, what do we get? 0. And is that good? Yes, it is. So formal charges, the preferred number is 0. So this further tells me that this is the correct Lewis structure for ammonia because it minimizes all of our formal charges. Note that I only did the formal charge of one of the hydrogens, but they're all identical. So all of them have 0 formal charges. All right. Okay, so let's do the same thing for formaldehyde. Let's see if we can do the same thing for formaldehyde. Okay. So it's once minus has, but first we need to split up the electrons in the bonds. Each atom gets half of the electrons in the bond. So I just remember each bond has 2 electrons, and then one of each goes to each atom. Right? So I just split up my electrons. I'll box everything. So there's a hydrogen, there's my oxygen, and then there's my carbon. So see how I'm careful to split those electrons in half to make sure only one electron from each bond goes to each atom, all right? And then this hydrogen's the same as the other one, so we'll just do it once. So in this example, we're gonna calculate the formal charges of 3 atoms, but we're still gonna do once minus has. All right, so let's go through this. Carbon once, how many electrons? And this is valence, so it's 4. Hydrogen, 1. Oxygen, 6. Okay. Hydrogen in this, or no, carbon, sorry. Carbon in this example, how many dots are inside that box? 4. Hydrogen, 1. And then oxygen, 6. Yes, where to get the 6 electrons in that oxygen box, 2 of the electrons came from the double bond that's there, but 4 of the electrons came from that lone pair. And so when we add all of this up, what do we get? A bunch of zeros. And is that good? Yes, it is. So that's why this is the correct Lewis structure for these molecules, because we minimize formal charges. And typically when you follow the 6 steps, that's what happens. It will automatically happen if you are trying to fulfill octets. You'll end up getting that formal charges typically add up to 0. But there are some examples where it doesn't, and that's where we move on to the next example. All right. I'll point out that this has business. A common mistake students do is, or with once, when we calculate formal charge, this is different than determining octet. When we did octets, we counted all of the bonding electrons around it, so it's different. Formal charge is a little bit different because we only count half of the electrons from bonding electrons, and we're subtracting it from the preferred number of valence electrons. So formal charge is slightly different from determining octets. All right, so let's do an example where formal charge will help us, and that's carbon dioxide. All right, so carbon dioxide, you might already know what it looks like because we've shown it to you a couple times in like chapter 5 where we did bond enthalpies and stuff. But let's, to a T, follow my 6 steps. So let me just copy it from over here. Copy. All right, let's do carbon monoxide or carbon dioxide and follow the steps exactly. All right, so I have a carbon and 2 oxygens. So how many valence electrons is that? 16? Okay, all right. All right, so that's valence electrons. I don't need to adjust for charge. So next, I write the skeleton structure. So it's my central atom. Carbon, yes. Carbon for 2 reasons. It's written first, and it's the most electropositive atom. So carbon's going to go in the middle. And then I'm going to draw the 2 oxygens. And then what else do I need to draw? Single bonds. Yeah, so just humor me. Don't let your brain automatically fill in what it is. I want us to get there via the 6 steps to show you where formal charge is useful. All right, so we drew our single bonds. How many electrons did I draw so far? 4, and I can spend how many more? 12. Okay, so where am I going to start putting electrons? On the oxygens first, and complete the octets while doing it. So I have 4, 5, 6, 7, 8, 9, 10. All right, that oxygen's done because now it has a complete octet, but now I have 6 more electrons, and I can do 11, 12, 13, 14, 15, 16. So I spent all of my electrons, all of them. All right, so now what do we do next? So we did outer electrons, so I have no more electrons to spend, so technically I can't put any on that central carbon atom. And I know that this central carbon atom needs more electrons because right now it does not have a complete octet. So we can't place electrons on that central atom. So this is where we use the last step, it's place double bonds if necessary. And so now it is necessary because that central atom is electron deficient. So right now, this carbon atom has only 4 of the electrons to complete its octet. So just thinking about it, how many double bonds or how many multiple bonds should I make to that central carbon atom to fulfill its octet? It has 4 electrons, it needs 4 more. So if I make 2 more bonds to it, won't I complete its octet? Yes. But there's an issue. There's 2 ways I can actually do it, right? I know what your brain wants to do, okay? I know what your brain wants to do. We need to make 2 more bonds to carbon. I feel like everyone in the room wants to do this, right? You want to do that? You want to do that? Yeah, so then you make 2 double bonds to carbon. But the issue is that carbon just needs 4 more electrons. They can actually come from anywhere. So couldn't I also just do this? Technically, I could. So let's just draw it and compare the 2, all right? So just humor me, okay? So I feel like most of us know what the correct one is, but again, just humor me. So when I move these 2 lone pairs on the oxygen atoms and make double bonds with carbon, now it will look like this. But on each of those oxygen atoms, how many lone pairs are on each of them? We still have 2. All right, so those didn't go anywhere. We only moved 1 of the lone pairs. All right, so if you count there, that has 16 electrons. All right, but then if we move to our second example where we kind of completed the octet a little bit differently, we have carbon there. We have a single bond. We didn't do anything to this oxygen. And we have a triple bond right there, an oxygen and a lone pair there. Okay, so let's look at these 2 structures. Do both of the structures have the 16 valence electrons I was allowed to place? Yes, yeah, okay. So they both have 16 electrons. Now check the octets of each of the atoms. Tell me, do any of the atoms not have a complete octet? All of them have complete octets technically. So how do we tell which one's correct, right? This is where we use formal charges. Formal charges will tell us which one is correct, because technically that has 8 electrons. 8, 8, 8, 8, 8. We don't technically, just using octets, don't know which one's correct. But the correct one does what with formal charges? Minimizes them. So let's go ahead and calculate the formal charges of all of them so we can figure out which one is correct. All right, so what's the equation for formal charge? Wants minus has. So oxygen wants how many electrons in its valence shell? 6. Carbon wants 4. Oxygen 6. So each of these, it's 6, 4, 6 across the board. Right? Has are the electrons that are actually drawn in the Lewis structure. So if what helps is, again, splitting the bonds. So the electrons are actually drawn and split equally across the 2 atoms. But with this triple bond, how many total electrons are right there? 6. So each atom is going to get 3 of those 6 electrons. All right? So I'll box it for easy readability. All right, so there we go. And then I'll box these guys. Oh, I didn't draw that box. Okay, so we count the dots in the box. Okay, so let's look at this structure first. How many electrons does this oxygen atom have? 6. Carbon, 4, and 6. So if we look at the formal charges, they're all zeros. Cool. Now let's look at the other one. This oxygen has how many electrons associated with it in its Lewis structure? 1, 2, 3, 4, 5. There are only 5 electrons there. But the middle carbon has 4, and then this last oxygen on the end here has 7. So when you add these up, or you subtract them or whatever, you get that one of the oxygens has a positive 1 formal charge. The central carbon is 0, and the other oxygen is negative 1. So this is why we see carbon dioxide is a carbon-oxygen double bond and not a triple bond and a single bond. Because technically, both of those structures, they had satisfied octets everywhere, but one of them is the most correct, and it's the one that minimizes formal charges. All right? Okay. Okay, so I think the next example is a little bit harder. I usually show CO2 because I feel like most people know that CO2 is a CO double bond. So let's do one where it's not as obvious which one, where the double bond goes, all right? So I hope you see why this one's correct. Again, it minimizes formal charges. Okay, let's do this one, the NCS anion. And I'm telling you that carbon's the central atom, all right? So if we go through the 6 steps, let's count valence electrons. So nitrogen, carbon, sulfur, it's an anion this time. So what are we going to do to the electron count? Are we going to remove an electron or add an electron? If it's an anion, we're going to add an electron. Yeah, because anions are negatively charged, so we have to add an electron to make it an anion. So we're adding an extra electron, 1 electron. So what does that add up to? 16? Cool. Okay. All right, so that's what I'm allowed to spend. So I draw my skeleton structure, and I already told you carbon is the central atom. So I got N, C, S, and I draw single bonds. All right, so I've drawn 4 electrons so far. I have 12 more to draw on, and so I'm going to put them on outer atoms first. Because our outer atoms are not identical, it actually matters which atom you put on electrons first. You always put electrons on the most electronegative thing, and then you work your way towards more electropositive. So in this case, nitrogen and sulfur, actually I don't know which one's more electronegative. No, nitrogen is more electronegative, yes. So we're going to put electrons on nitrogen first. So we have 4, 5, 6, 7, 8, 9, 10. Right now nitrogen has an octet, so let's move on to sulfur. 11, 12, 13, 14, 15, 16. Okay, so now they both have complete octets. And actually, in this example, it didn't matter which one you started on because both of them will get 6 in the end anyway. But sometimes it does matter, so do keep that in mind. All right. So this structure kind of looks similar to our CO example. The CO, this example, it looks kind of similar, where we have a electron deficient central atom, but complete octets on the outside, right? So this carbon atom is electron deficient and only has 4 electrons. It wants 4 more electrons. So how many more how many more bonds should I draw towards it? 2 more. But can you see all the different ways I can draw 2 bonds? There's a bunch of different ways. So we need to figure out which one is the correct way to complete the octet of carbon. There's a bunch of ways. So I'm going to redraw this 1, 2, 3 different times. So carbon needs a complete octet. So one of the ways I can do it is move 2 of the lone pairs from nitrogen to make a triple bond. How else could I complete it? You could do it like CO2 and you could do 1 from each. We can do 1 from each. So 1 lone pair from nitrogen, 1 lone pair from sulfur. And what's the last way I can complete the octet? 4 electrons from sulfur instead. All of these technically will complete the octet of carbon. So let's just draw it. So in this example, if I redraw this, nitrogen has a triple bond. I'm left with 1 lone pair, carbon, sulfur. Right? The next one, we have nitrogen, a double bond, carbon, and then another double bond to sulfur. 2 electrons, 2 lone pairs on each. And then the last one, the triple bond is going to go between carbon and sulfur. So nitrogen, carbon, triple bond to sulfur, 1 lone pair there. These 3 stay there. Okay. Look at every single atom. Is there any atom that does not have an octet? Or do they all have octets? They all have octets. So can we tell which one's correct? Nope. So what do we got to do? Formal charge, yes. Formal charges will tell us which one is correct. All right? So, because technically they all look kind of good. They all look good. They all look good. But formal charge will tell us which one is the most correct. So the equation for formal charge is once minus has. So once comes from the periodic table. All right? So nitrogen wants how many electrons in its valence shell? 5. Carbon once. 4. Sulfur once. 6. And so it's 5, 4, 6 across all of these structures. 5, 4, 6. 5, 4, 6. What differs is has, because has comes from the Lewis structure. All right? So the idea here is for each atom, count all of the non-bonding electrons, count all of its lone pairs, but only take 1 electron from each bond. All right? So if we look at nitrogen, it has a triple bond, but we're only taking 3 of the electrons from the triple bond. So nitrogen has how many electrons in this structure? Do I need to box it? Count those. 5. Carbon has how many? 4. So again, I can draw it. Okay, so I'll box it. So count all of those, and then sulfur has that many. So how many does sulfur have? 7, all right? So let's keep going. This nitrogen has how many electrons assigned to it? 1, 2, 3, 4, 5, 6. So 6. Carbon has 4. Sulfur has 6. Great. And then this last one. Nitrogen has 7. Yes, because 1 of the electrons from that bond. Carbon has 4. Sulfur has 5. All right, so let's go ahead and subtract those and see which one's right. So this first structure is 0, 0, -1. The middle one is -1, 0, 0. And then the last one is -2, 0, +1. Okay. So is there a structure we can eliminate right away? The last one does not minimize formal charges. Only has one atom with a 0. The other two, basically, I can put the negative charge on the nitrogen or the sulfur. But this third one, there's multiple negative charges, or multiple charges, so we don't want that one. That one's wrong. Okay, so we have a choice. We can put the negative charge on sulfur, or we can put it on nitrogen. Which one do we want to put it on? I know 0 is preferred, but we can't have a 0 in this structure. We have to have a negative somewhere, but we have a choice of where we want to put it. And so remember what the rule was? It was if you have to have a formal charge, especially if it's negative, you put it on the most electronegative atom. So let's look back at this structure. So where do we want to put it? On the sulfur or on the nitrogen? On the nitrogen. So which structure is the correct one? It's the middle one. It's the middle one. All right? So that's how we got there. All right? You follow the 6 steps. They work every single time. Sometimes there's multiple ways you can complete a octet of your central atom, especially with like double bonds and stuff. And that's where sometimes formal charges are required to determine which of those structures is the most correct one. All of these technically obey the octet rule. But it's only the central one that optimizes formal charges. So that's the big difference there, all right? So never do you have to spray and pray electrons like I've done in the past, all right? So inventory your electrons from valence electrons. Those are the electrons you are only allowed to place. Sometimes your central atom will be electron deficient. That's when you start making double or multiple bonds to try to complete that octet. You can move electrons around, but you can't add any more from our initial valence electron count from the beginning. All right, so those are our Lewis structures. Do make sure you practice those 6 steps. I have a ton of practice problems in the overview sheet. All right, the 6 steps work every single time. Okay, so let's look at some other types of Lewis structures where it may seem like there's more than one correct answer. So this is the idea of resonance structures. Sometimes there's more than one valid Lewis structure when you draw it. So here's an example, ozone, O3. So if you count the valence electrons, there's 18 we have to spend. And so I already went ahead and did the six steps. All right, I only did 5 steps. So I drew all the oxygens, and I drew in all 18 valence electrons. But the last 2 electrons that I placed were right here on the central atom. But I didn't have another 2 electrons to complete the octet. Those are all 18 of my electrons. So in order to make that central oxygen have a satisfied octet, I need to make a double bond to it, right? If I make a double bond, it'll complete that octet. But here's the question. From what atom am I going to make the double bond? It doesn't matter, right? It's a symmetrical molecule. Some of you might think, oh, put it right there. But maybe the person next to you is like, oh, put it right there. Put it right there. So actually, you're both correct, all right? That the double bond can be made from either of those oxygens. So instead of the double bond just coming from one oxygen, it's actually going to come from both. And that's the idea of a resonance structure, that we can complete this Lewis structure 2 different ways, and both of them are valid. So in the pink structure, like the pink arrow puts the double bond right here. The green arrow puts the double bond right here. Both of these structures are correct. So what happens is that ozone is actually a combination of both of those Lewis structures, that we don't have a short double bond and a long double bond in ozone. If you actually look at a molecule of ozone, you actually have two bond lengths that are the exact same, because you basically have a smearing effect of those two electrons from the double bond across both sides of this molecule. And that's the idea of resonance. And that is a very, very important concept that'll come back in organic, where we are able to spread the two electrons that are in this double bond right here across two different places, right? So they exist actually on both sides at the same time. What doesn't happen here is it's not that this molecule is flipping back and forth. It's not like the double bond is flipping back and forth. No, the electrons actually exist on both sides, all right? And so what we call this is a delocalization of electrons, and what happens is it really stabilizes this molecule, all right? Resonance is a very stabilizing force because we're moving around electron density, so it's not isolated in one spot. So let me show you kind of the experimental view here. So again, I mentioned that ozone, if you look at a molecule of ozone, you're not gonna find a short bond and a long bond somewhere. You're gonna see actually two bonds that are identical in length, all right? So you're not gonna see a double bond and a single bond. So we can actually calculate the bond order of this molecule is somewhere between that of a single bond and a double bond. Ozone has a bond order of 1.5 because of that smearing effect of electrons, that the double bond exists on both sides at the same time. So how we can calculate the bond order of something that undergoes resonance, this is how I do it, all right? You look at the number of bonds involved in the number of places that you can place this double bond. So I see, oh, there's a double bond involved, it's swapping places with a single bond. So in this case, there are 3 bonds that are moving around. But then I ask myself, how many positions can I put those two different bonds? I can either put it here or here. So there's 3 total bonds moving around 2 positions, and that's how I calculate bond order. So in this case, the bond order for ozone molecule is 1.5. Each of those bonds is slightly stronger than a single bond, but not as strong as a double bond. So that's where we get the 1.5 number. Number of bonds involved over number of positions. All right, so those are our resonance structures. This is applicable for molecules that have more than one valid Lewis structure. There's more than one way to complete the Lewis structure and it be completely correct. All right, so this doesn't have to do with formal charges as much. All right, okay, so let's look at another example, nitrate. All right, so let's go through the 6 steps and look at nitrate. So nitrate, 5 from nitrogen, 3 oxygen, so 3 times 6, and it's an anion. So what do we do? Add an electron or remove an electron? Add an electron. So we're going to add an electron. So that adds up to what? 24? 24? Yeah? Okay. All right. So those are our valence electrons. So next we draw our skeleton structure. What's my central atom? Nitrogen. Cool. Then I draw 3 oxygens around it. All right, I drew single bonds. Okay, so those are 6 electrons. So that means I have, 18 more electrons to put on. So where am I going to put them? Outsides, then inside. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There we go. All right, so those 18 electrons fulfilled the octets of oxygen. Am I done? No, because what's wrong with my central atom? It don't have an octet. It only has 6 electrons. So I need to make a double bond, right? But from where? It doesn't matter. Well, it kind of matters. Okay, if you ask the person next to you, they might be like, oh, I want to bring these 2 electrons down. And they would be right. Doing that would complete the octet of the central atom. But someone next to you might say, no, I want to move those electrons, right? Or someone else might say, oh, I want to move these electrons. All of you are correct. So basically, I can put the double bond here, here, or here, and all of those are correct. All of them have the same formal charges. All of them have complete octets. Yeah?
So bond order is different than resonance bond order?
So remember I said that there are 3 ways to calculate bond order. This is the second way to calculate bond order. So like, for example, if I just wrote this, you would tell me what kind of bond is that? A single bond. If I drew that, that's a double bond. If it was that, it's a triple bond. Calculating bond order is a little bit different and only specific to the way that we just did it right here is only specific to things that exhibit resonance. It's a little bit different. Okay, so let's just keep going. All right, so we can put the double bond in any one of these places and they are all correct, and that's what is in this picture right here. All right, the double bond can be completed in all 3 positions. It's not that the double bond is flipping between all of the positions. Instead, the double bond actually already exists across the entire molecule, all right? That we're just smearing those extra electrons across the entire molecule, all right? So these are the 3 resonance structures. So if we look at them, does every atom obey the octet rule? In all, how many atoms are here? 12. Do all of them have complete octets? Yes, they do. Yes, they do. So they are all correct, and all of them have the exact same formal charges in all of them. All of them have like 2 oxygens with -1s and a nitrogen with a positive, but they just move around in different places, but they're all equivalent in terms of formal charges, all right? So with what we understand with resonance, what are we going to see when we look at a nitrate molecule? Are we going to see a short bond and 2 long bonds, or are we going to see 3 bonds that are all the same length? 3 bonds that are all the same length. So let's go ahead and calculate bond order. So what we want to do to calculate bond order for resonance structures is just look at one resonance structure. Just look at one of them and think how many bonds are moving around. We have a double bond and 2 single bonds that are all swapping places. So there's a total of 4 bonds that are moving around. But then how many positions is that double bond moving around? 3. Or you can think number of positions is number of resonance structures. So it's the number of valid Lewis structures I can draw. It's the number of pictures that I have that are there. All right. So what do we see the bond order is for nitrate? 1.33. Yes, it is 1.33. So what we'll see for a nitrate molecule is that we have an NO bond that is a little bit longer than or a little bit stronger than a single bond, but not as strong as a double bond, all right? Okay, so yes, I'll point out, remember I said that there are 3 ways to calculate bond order. This is the second one. The third way we will talk about in chapter 9. And they're all a little bit different, but they all talk about the same thing. As bond order increases, bonds are getting stronger and shorter. Okay, so let's talk about some exceptions that I mentioned before. Boron and beryllium. All right, so if you have a boron containing compound, boron is fine with 6 electrons. All right, boron, because it's really small, doesn't need a complete octet. It's happy with 6. So BF3 just has all single bonds to it. Same thing with beryllium. Beryllium is fine with 2 valence electrons. Also, beryllium is kind of metallic. I don't know why they put that here, but for example, beryllium dichloride looks like this, and it's fine to be like that, right? It's fine with 4 electrons. So that's one exception to the octet rule. The second exception is anything with an odd number of valence electrons. If you have an odd number of valence electrons, it is impossible to make all atoms have an octet of 8. It's impossible. So we will never give you an odd number of electrons, okay? We never give you an odd number, okay? So that means if you're doing your electron count and you calculate an odd number, you messed up, all right? And you should try again, because we'll never give you an odd number. Okay, so that would be this example. An odd number, you can't fix it. All right, but the third one we can figure out. The third type of Lewis structure exception is any elements that are really heavy. So period 3 elements and heavier. These elements, they're big enough that they can actually exceed their octet. So remember when we talked about the octet rule, we said that it works really, really well for period 2 elements, carbon, nitrogen, oxygen, fluorine. But anything heavier than that, these atoms can actually accommodate even more electrons to them. And so we see that where, like, if you look at this sulfur atom, it doesn't have 8 electrons around it. It has how many? It has 12 because there's 6 bonds to it. Each bond has 2 electrons, and that's completely fine. This is a valid Lewis structure. This is also a valid Lewis structure. Yes, this is xenon, the noble gases that don't react with anything. This is actually a real compound. This xenon also exceeds its octet, and that is completely okay because it is a large, it's a really large atom, and once they get really large, they can accommodate having chemical bonds. And so in this example, the reason SF6 does exist, sulfur can exceed its octet, all right? Sulfur has 12 electrons around it, but let's for funsies calculate what is the formal charge of that sulfur atom. Sulfur wants how many electrons from the periodic table? 6, but then how many electrons are actually assigned to it on this Lewis structure? 6, so its formal charge is 0, and that's a good or bad thing? That's a good thing. So that's why this is a valid Lewis structure. Sulfur can accommodate more electrons, exceed its octet. Also, it puts a 0 formal charge on it for this structure. All right, so let's do a period 3 element as essential atom. Okay, it still works. The rules are the exact same 6 rules. Okay, just know that the essential atom can exceed its octet if it's period 3 or heavier. So let's do SF4. Okay, sulfur has 6, 4 fluorines have 7. What does that add up to? 20, 28, 34? 34? Can I get a nod? Yes, thank you. Yeah, all right. Okay, so it's the same exact steps. I have 34 to spend. I put the sulfur in the middle. I draw single bonds to all the fluorines. Okay. Next, what do I do? Put electrons on the fluorines. But you got to count very carefully, because already, how many electrons have I already drawn? 8, because of those single bonds. So 8. Whew. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Where do those last 2 electrons go? On the central atom. And is that allowed? Yep, because sulfur is a period 3 element. Yep, and so that is the correct Lewis structure. If you calculate the formal charge of everything, what do you think it'll be? 0 for everything, all right? Okay, so you got to count really carefully, because if you miscount, then you will put the wrong number of electrons on that central atom. All right, so let's do BrF4 anion. So this is 20, 30, an anion, we're adding an electron. Is that 36? Okay, 36? Wait. Yes, it's 36. Okay, so same thing. Bromine in the middle, 4 fluorines. We need to count very carefully. So I've already drawn 8. 8 electrons, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And so how many electrons go on that central bromine? 4. So we put them in pairs. 1, 2, 3, 4. That's what it looks like. Count very carefully. See, the 6 steps, they work every time. Every single time. Yes. Okay. So those are our Lewis structures. Memorize those 6 steps. Okay, I've been mentioning before, we've been talking about bond order, right? Single bonds, double bonds, triple bonds. As bond order goes up, strength goes up, but length does what? Goes down, yes. All right, so as bond order goes up, We're adding more electrons to attract these two atoms to one another, so that brings potential energy down. So it's harder to rip those two atoms apart. So we'll see high bond enthalpies for single versus double versus triple bonds. Then that's what we see here. We talked about, bond enthalpies back in chapter 5. You might have noticed that single bonds were typically weaker than double bonds, vice versa, or, and et cetera. And so that's what we see here. And the reasoning is because there's more electrons pulling those two atoms together. All right, so you see here's the energy of like a double bond and a triple bond for carbon. Or for nitrogen, a single bond to nitrogen and oxygen is 200 kilojoules, but a NO double bond is 600 kilojoules. So with that information, tell me, this is nitrate, right? Nitrate. What is the most likely bond enthalpy? If we measure the bond enthalpy of the NO bond in nitrate, what do you think you will measure? So look at the two bond strengths I highlighted. So NO single bond is 200 and NO double bond is 600. So are you going to measure a bond strength of 200 and 600 in nitrate, or will you measure something else? What's special about nitrate? Does it actually have a bond order of 1 and 2? No, what's its bond order? It's like 1.3. So what are we going to measure if we measure the NO bond strength in nitrate? We're going to actually measure C, a bond strength of about 400, because this is equal to something stronger, stronger than a single bond, but not as strong as a double bond, because our bond order, remember, is kind of like this weighted average of all of the, having the double bond in a lot of different places here. So we're gonna just see a bond strength between that of a single and a double bond, because the single and double bond don't exist discretely on that molecule, all right? Okay, and so that's the trend with bond order there. All right, so let's look at some, because resonance always freaks students out. All right, so let's look at the resonance structures of benzene. All right, so benzene is a ring of 6 carbon atoms where there are alternating double and single bonds. All right, so let's just, I'll show you. So the alternating single and double bonds, if we kind of look at these two resonance structures, they can either occur in these 3 locations or these 3 locations. It doesn't really matter. It's like almost like we're kind of like rotating where those double bonds are, if you see that. So let's see if we can't calculate the bond order of a carbon-carbon bond in benzene. Maybe you already think you know what it is. You see, oh, it's alternating single and double bonds, so the bond order is going to be between those two. So, but let's use our equation here to calculate what the bond order is. So if we think about the total number of bonds that are involved here, there's 3 sets of double bonds and 3 single bonds. So to me, that's a total of 9 bonds. But then how many positions are they moving around? There are 6 different positions. There's 6 different carbon-carbon bonds total within there. So 9 divided by 6 equals 1.5. Yes, it's 1.5. So hopefully, you kind of inferred that, oh, alternating single and double bond, it's going to lie, the total bond order for this resonance structure will lie in between. Yeah. Yeah, if we go here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 bonds. And if you count all of the different positions that those 9 bonds are moving around, there are 6 different positions that they're moving around. All right, and so what we're saying here, because the double bond exists in 6 different positions, that those electrons are completely delocalized. And again, because of the delocalization of electrons, we see bond strengths that are between that of a double and a single bond. Historically, benzene was a really interesting molecule, because for a long time they did think it was like alternating single and double bonds, until a chemist named Kekulé, I think the story is, and I don't know how true this is, he was like high on opium. And I think he was really rich. And so he was in a carriage, just like high on drugs. And he looked out of his carriage to see another carriage. And he was looking at the wheel of the carriage, all right? And he was, again, high. And so he looked at that carriage wheel and was thinking, oh, maybe that's what the electrons do in a benzene ring. Because the idea is that those electrons, those 6 electrons that are in the double bonds on our benzene ring, they're not in isolated places. They're actually smeared across the entire molecule. So it took some opium and like a carriage ride for Kekule to figure that out. This structure is actually called a Kekule structure, so it's named after him. I don't know how true that is, all right, but you know, I think it's fun. So that's the whole idea, that these double bond electrons, they're smeared or delocalized across the entire molecule. All right, so is this the last? It is the last slide. Yikes. I thought we weren't going to finish. Okay, so resonance is always an issue, a tricky issue for students, but I want you to recognize the patterns. Not everything's going to undergo resonance. Only certain things undergo resonance. Usually oxygens, sulfurs are involved. It's usually oxygens and sulfurs that things undergo, usually it's oxygen for us, where things undergo resonance. So these 3 molecules all undergo resonance, and I want you to see what's the common feature here in these resonance structures. So carbonate undergoes resonance, acetate, sulfate, all of these undergo resonance. So let's first calculate the bond order of all of these things, all right? So here, the double bond between carbon and oxygen and carbonate goes right here, but is there other places I could put that double bond? Yeah, couldn't I also put the double bond there and there? Yes, so let's calculate the bond order. What is the bond order? So this double bond can go there, there, or there. So I'm moving around a double bond and 2 single bonds. So there are 4 bonds that are moving around. How many positions? 3. So this carbonate has a bond order of 1.33. Cool, just like nitrate. Okay, let's do acetate. There's the double bond. Does it have to be right there? No, where else could it be? Right here? Could I put the double bond right here? Right here? No, I can't put the double bond right there. I can only put the double bond right. This carbon already has a satisfied octet, all right? So I can either put the double bond here or here. That's it. So this resonance structure has a bond order of how many bonds are moving around? 3, because there's a double bond here and a single bond there, over how many positions? 2, so this is 1.5. So do not count that bond. That carbon-carbon bond does not participate in resonance. That's already satisfied. All right, so in these 2 examples, what are the atoms undergoing resonance? It's always oxygen. It's almost always oxygen. Let's look at this one. Okay, and looky there, it's oxygen again. Okay, so look at these double bonds. They're right here at the top and the bottom. There's a bunch of places that I could put those 2 double bonds, right? I could put them here, I could put them here, I could put them, the 2 here. I just need 2 double bonds and they can be in any one of those 4 positions, right? So what is the bond order? How many bonds are moving around? Yeah, 6. 1, 2, 3, 4, 5, 6. Yeah, 6 over how many positions? 4 different positions. Yes, there's 4 different positions. There's 4 different combinations of where I can put the double bonds. So this has a bond order of 1.5. All right. Okay. So let's look at, so I hope, do you see the commonality of all of these? It's always oxygen, and it's an oxygen typically with a negative charge on it. That's what undergoes resonance. So can formaldehyde undergo resonance? What's the thing we're looking for? We're looking for a double bond that we can put in different places that are identical. So formaldehyde, even though it has a double bond, cannot undergo resonance. So what is the bond order of the CO bond in formaldehyde? Will you use our bonds over positions equation here? No. This just has a bond order of 2, and that's it. All right. So that's That's chapter 8. I have to make a decision about homework, because technically homework would be due on Monday. Let me think about it. Absolutely chapter 7 is due. Absolutely chapter 7 is due. But I need to think about 8. Okay, read it in my recap.